Okay, yeah, no problem. Hey guys, I really apologize for the technical delays here. Okay, there we go. I see it now. All right, thanks, Brett. Bye. All right, guys. Well, hey, welcome to the wild world of IT, where things go well and things go wrong. So we're gonna just start this bad boy back over. Bear with me for a second while I do that. I'll just move back through the material. All right, so again, I truly apologize. I thought I was live streaming. It turns out I was not, so the experience of talking to an empty wall proved to be exactly the way I thought it would. I didn't have the feedback I needed to make a correction. So, hi, welcome. I'm Ryan Cloutier. I'm glad to be your instructor. Looking forward to having this class with you guys tonight. I am going to go ahead and show you the crowd. So that is the crowd that I have up to help me. Matter of fact, they helped me so much I didn't even realize I wasn't live streaming. So again, my apologies for that. Before we get into class 4 tonight and really dive in, I do want to go over some quick housekeeping with you. So just as a friendly reminder, please do keep the on live chat, keep it clean. We're adults here. Try to keep it focused on the course content. Everyone appreciates a good dad joke, myself included. However, I won't be able to see them tonight, but do try to, keep it focused on content. At no time are you to use the chat for anything that would be disrespectful, offensive, obscene, indecent, or anything like that. So please just, again, be adults, and then no discussion of politics or religion. It's just too sensitive, and it'll distract you from this awesome material you're about to learn. So thank you. Checking in, we're all the way through chapters 1, 2, and 3, and we're part of the way into chapter 4. Please, chat with the moderators and let them know, how many of you have read chapters 1, 2, and 3. Let them know your questions. They'll try to get them to me as best as they can. I'm actually turning up the volume on my phone in the event that I'm needed, so I do apologize if that makes noise. I'll try to mute it quickly, but I wasn't able to tell I wasn't online, and so I got the phone turned up now, Brad. Call me if anything else goes wrong. We have slightly over 112 slides tonight, and the reason for that is I wanted to take a moment to talk to you guys about some study tips. Learning this material is pretty difficult. When I went through this experience and I was learning this material, as I'm sure the experience you guys are having, a lot of this is really heavy stuff. It's a lot of memorization. It might be pretty dry. Hats off to Brad for walking us through last week or on Monday, taking us through the security models. That's a tough topic. It's a dry topic, right? So some of the tips that I've used to help myself, retain this information and just generally be better at learning is that I try to study in small amounts, and I try to do that frequently, 20 to 30 minutes per study. And the reason I do that is it gives me a chance to walk away, take a break, think about and ruminate, if you will, on what I've learned. The other technique that I use is that I use flashcard apps. And practice tests on my phone. So when I have those little moments of downtime, when I'm, post or pre-COVID, when I was waiting in line at the store, or I'm, doing, activities out with people, and maybe my wife is shopping at Target and I've got another half an hour to be here and nothing left to see, then I jump on my phone and start to study. The other thing that I encourage you to do is after you've learned something really heavy, you're going to want to take a nap if you can. It actually helps you with memory retention. There are studies that show the psychological impact of memory retention when you learn something and you sleep shortly after learning. It's a great tactic. It works well. If the security models put you to bed, I don't blame you. Tonight, I'm going to try to keep it a little lighter, but the topic is kind of heavy. We're going to be talking encryption and some other things, cryptography. So just, try to stick with it. Write things down. Another technique I use is to write it down, to read it back, to say it out loud. Because now I'm processing the information in several different ways. I'm not just taking it in visually. I'm taking it in written form by actually having to write it. I'm hearing it. I'm taking it in as audio form. I know all of you have different learning styles. So try to mix it up. Try to expose yourself to this information in several different ways. It'll definitely help you with retaining it. The other thing I'm going to want to encourage you to do is to use the study group. The study group, it's just been amazing. I've seen so much great activity over the last week. I've been monitoring it. And I apologize, I don't remember the student's name. I'll look it up and contact you. But one of the students provided these mind maps. And these mind maps are amazing. They kind of show you the key areas, if you will, and the relationships. So super cool that you did that. Thank you so much. I actually am going to be using them myself just as a refresher and a reminder. Try to exercise. Exercise and fresh air in between your study sessions. It can do so much. It can lower your stress. It can, according to certain studies out there, it can improve memory. And it feels good. I don't know how you as individuals feel, but I know myself, after I get done learning a lot of really heavy stuff, I'm like, oh, I'm so tired, and I just feel it. And if I go do a little bit of yoga, a little stretching, I just feel so much better. So that's kind of my tips for you guys. If you haven't already signed up for the study group, please do. This is the address that you can register at. And if you're looking for practice exams, FRSecure.education has some great stuff available, so check that out. You guys are doing fantastic. You showed up tonight. That says a lot. We've already covered some domains, including the introduction, right? Evan did a great job there. He did a great job taking us through security and risk management, asset security. That's so foundational. That's why it's domain 1 and 2, right? It's kind of the beginning. Fantastic job by Evan there. Brad did a wonderful job taking us through security engineering. We did cover that up to evaluation methods, certification, accreditation. We're going to be picking up where we left off. But before we do that, as promised, I do have a quiz for you guys. So no cheating. I know you guys all have Google open in the other screen, but try not to cheat here. What type of memory is often used for CPU registers? Is it DRAM or DRAM? And I just learned today, thanks to my son, that DRAM is also a wrapper. I did not know that. Is it firmware? Is it ROM? Or is it SRAM? Well, as I look at this, I know that firmware software, so I can probably eliminate that one. And I know that ROM means read-only memory, so I can probably eliminate that one, which only has me down to DRAM or SRAM. And the correct answer here is SRAM, static random access memory. Primarily, this memory is used for caching on CPUs, and we'll get a little bit more into what is CPU caching later on here tonight. This one was a popular one in the chat on Monday. What was ISO 17799 renamed as? Was it BS 77991? Was it ISO 27000? Was it ISO 27001? Or was it ISO 27002? And I'll be curious to moderators, keep an eye on the chat if we're actually getting answers to this. I would love at the end to find out kind of what people had said. So in this case, it is ISO 27002. Now, what's important to understand here is that ISO 27002 are the best practices, and ISO 27001 are the standards. So they kind of work hand in hand. And again, remember 2002 are best practices, 2001 is the standard, and 17799 was renamed to ISO 27002. Which of the following describes a duty of the data owner? Is it the data owner's duty to patch systems, report suspicious activity, ensure the files are backed up, ensure the data has proper security labels? So, again, as I look at this list, I like to do a process of elimination when I'm taking an exam, because I know at least one of the questions in a multiple choice is going to be completely wrong. And in this case, reporting suspicious activity, I understand to be the responsibility of everyone. So I'm thinking it's probably not that. Patching the system sounds more like a systems operation, so I'm thinking it's probably not that. Backing up of data also sounds like it might belong to systems or IT, so I don't know that it's that. Ensuring the data has proper security labels. That is the correct answer. It is the responsibility, and they have several, but it is the responsibility of the data owner to ensure that data is properly classified and identified. So that they need to be the ones to say this data is secret, this data is confidential, this data is private, this data is public. That is ultimately the responsibility of the data owner. Next question in the quiz. Which control framework has 34 processes across 4 domains? So if we remember from our studying, different frameworks have different amount of processes and domains. In this case, it's just important to know that COBIT is the one that has 34 processes across 4 domains. As you take the test, you will see questions like this. So just try to remember those things as much as you can. They will ask you specific things. This is the correct answer. I forget how many processes. And just for a refresher, COBIT stands for Control Objectives for Information and Related Technology. And they were defined to assist in the planning and organizing, acquiring and implementing, delivery and support of information technology. Question 5. Which managerial role is responsible for the actual computers that house data? This is including the security of hardware and software configurations. So again, in the question, there's some clues, right? Is it the custodian? And I think here we mean data custodian. However, maybe it is the real custodian. It's the janitor of the building. Is it the data owner? Is it the mission owner? Or is it the system owner? Well, we know Evan is the owner of the mission, and so that's probably not the right answer. I look at the question, I see a lot of things that are related to systems. So it is the system owner. Hardware and software configurations are the responsibility of the system owner. Question 6 here. What type of relatively expensive and fast memory uses small latches called flip-flops to store bits? And remember, these flip-flops are electronic flip-flops, not the kind you wear on your feet to the beach. So DRAM, EEPROM, SRAM, or SSD. Well, I remember that SSD is a hard drive, so it probably isn't that one. And DRAM, I think, doesn't have flip-flops, so it might not be that one. EEPROM is electronically overwrote. SRAM, maybe it's one of these two. The correct answer is that it's SRAM, static RAM. It's important to understand, and the key here in the question is flip-flops. The flip-flops is the giveaway for the type of memory that it would be. Just like in this question, it says what type of memory stores bits in small capacitors? Capacitors are similar to like tiny batteries. You find them on all kinds of electronics. They basically store some energy and then dissipate it. So is it DRAM, EEPROM, SRAM, or SSD? Well, in this case, it is DRAM, or as the rest of the world pronounces it, RAM. When you go to Best Buy or you go to Micro Center or Amazon to buy RAM for your computer, almost always you're purchasing DRAM. It is the most common type of memory found in personal computers. So with that, we're going to move in. I'm just going to check on my moderators real quick. All right. Am I pacing okay, guys? We're doing okay? Looks like we're doing all right. Okay, here we go. So I'm going to speed up just a little bit because I do want to respect time, and unfortunately lost some on the beginning here. So Chapter 4, diving in. We're going to talk about secure system design concepts, secure hardware architecture, secure operating system and software architecture, virtualization and distributed computing, system vulnerabilities, threats, and countermeasures. These used to be separate domains of security architecture, cryptography, and physical security, but we have put them together. We're taking 3 classes to get through this. You're on class 2 of 3. And remember that thing I said about naps? You might need one at the end of this. So we're going to start on page 116 this evening, and we're going to talk about layering. And layering is a concept in security that's really important to understand. Also remember, orange things matter, right? So layering, being an orange word, you really want to study this. Think of security layering like an onion. The more layers that you have, the more steps there are between the bad guy and what you're trying to protect. But layers also create complexity. So we'll talk more about that later on. But layering essentially is what you do to protect your system. Firewall is a layer, application layer, hardware layer, kernel layer, operating system layer. Definitely study up on the OSI. I can remember that was very much a question that came up a lot during my practice exams, and I think it was even on the real exam. So know the OSI model, it matters, and it helps you to understand layering. Another concept you want to get your head wrapped around is abstraction. Now, abstraction can make it more difficult to secure systems, and as you can see, complexity is the enemy of security. But abstraction is needed a lot of times to protect our users. So if you see the example, and I'm not going to read every word because I do want to respect time, but basically an end user listens to an MP3. All of the things that happen before that are abstracted from them. So all the computer computations that are happening and all the data that is flowing through the system and going in and out of the CPU and memory, that is all abstracted from the user. They simply just hear the music. So now we're going to talk about one of those layers. We're going to talk about the ring model. And the ring model is how CPU hardware layering is used to separate and protect the domains. And by domains, we just mean the different areas and things. I've got a graphic in a second that'll help explain that better. So basically, most Intel x86 processors, they have 4. So we have ring 0, and for any of you familiar with software development, right, 0 is where we start. It's actually 1. But we have ring 0, ring 1, ring 2, and ring 3. So it's the kernel, it's the operating system, device drivers, and user applications. And then processes are what communicate between the rings that allow the data and calls for hardware and things like that to happen. System calls are generally slow, but performing work across rings, performing work in a single ring provides a greater degree of security. The ring model also provides us a degree of abstraction. You remember that from the previous slide. Linux and Windows use rings 0 and 3 only. And then as we get into virtualization, hypervisor mode allows virtual guests to operate in ring 0, which is one ring below. So think of it as ring -1. So here you can see the kernel is the most privileged of the rings. That's where the highest amount of permissions exist to interact with the hardware. And then as we move out away from the kernel, we have our device drivers. And then we have another layer of device drivers in ring 2. Some systems use that, some systems don't. And then ring 3, which is our application layer. And in the case of Windows, like we had mentioned, they're operating in ring 0 and ring 3. The ring, as in Lord of the Rings, lock it away, right? Another technique that I use for learning is to associate something visually. So now we're going to talk a little bit about open and closed systems. Open systems are exactly that. They're open. Most Windows PCs, Android cell phones, these are open systems. You're able to intermix different manufacturers' components. You can intermix different manufacturers' software. It's a very open thing. And then closed systems are generally proprietary hardware and software. And the most common and famous closed system in the market today is Apple. Apple products are considered a closed system, or what we call closed architecture. So now we're going to give you the Computer 101, system unit and motherboard. So the system unit is everything inside the computer case. It's all the guts and parts and wires and connections. The motherboard is going to be that big giant computer board that takes up the majority of the case. And I've got some pictures for you in just a moment. The motherboard is like the heartbeat of the computer. It controls the actions of all the other peripheral devices that we have in there, things like video cards and keyboards and monitors and so on and so forth. So this is a basic overview of a system. This is a little dated. If you were to go buy a brand new one today, it probably isn't coming with a CD drive. Some of them still do, but a lot of them don't. But what you've got is your power supply, you've got your fan, you've got a video card, some kind of way to connect to the internet, modem, a network interface card, something like that. You've got a sound card, generally speaking. And then you have, the ribbons and cables that kind of connect everything up, and then obviously your hard drive. We're going to take a little bit of a closer look at a motherboard. And this will all be sent out later, so don't worry about memorizing this. I don't recall anything on the exam that gets deep into this. But one thing that's important to understand about the motherboard is things like, where does the CPU live and what's a north bridge and a south bridge. These things will be on the test. This is a visual to help you see where those are. This is your north bridge, and this is your north bridge, and this is your south bridge. This is going to be where your CPU lives, and this is where your memory goes. Most computer users, that and a video card, maybe a sound card, and they're good to go. So study this when it comes out. The other thing to understand is that, again, the motherboard is the heart of the computer, if you will. So as power flows in through the power connectors, that power is then controlled and distributed by the motherboard to the video card, to the memory, to the CPU, and so on and so forth. So we're going to move on to computer bus, and computer bus is kind of what it sounds like. It's a bus, right? It's how something moves from the CPU to the memory to the input to the output, keyboard, mouse, right? So as we interact with the computer, those things, those commands need to get themselves to the processor, and the means by which they do that is through the computer bus. So if we look here back to that north bridge that I spoke of, the north bridge is going to handle video, RAM, memory, and CPU. Almost exclusively, that's what flows through the north bridge. And then the south bridge handles the other stuff. Extra cards, sound cards, and maybe you got a Wacom pen or something like that. USB, all that stuff's going to flow through the south bridge. You're going to have the hard drive's going to flow through the south bridge. And the reason for that and why they're separated is to allow for higher performance of communication between the CPU and the memory bus and the AGP bus. If all that was flowing through the same bridge, you'd get bottlenecks. So North Bridge is also called the memory controller hub. It connects the CPU to the RAM and to the video memory. So as you can see, so it's faster. And then South Bridge controls all the other stuff. So with that, let's talk a little bit about the central processing unit. And hopefully I'm not moving too fast for you guys. If I am, let the moderators know. So the CPU really is the brains of the computer. This is the part where all the math is happening, all the calculations and decisions and all these things are going on inside of the processor. And the processor is rated in number of clock cycles per second. So when you hear somebody say 2.4 gigahertz Pentium 4, what that translates to is that that processor is capable of executing 2.4 billion clock cycles per second. Mind blown, right? That's a huge amount of stuff happening in literal blink of an eye. So this is a look at a processor. This is what it would look like if it was installed on the board without a heatsink. This is what it looks like before you install it. And I wanted to give you guys another quick little look because we do have an i7 here. So this is what it looks like inside. If you could actually look inside the processor, what you would see is that it has these cores. That's where you hear people talk about cores. And then it's got its own memory. So remember we were talking about that CPU register, right? So CPU has its own memory inside of it. And this is what they call the shared L3 cache. And then there's a controller for interfacing with the memory. And then there's another piece over here for PCIe, which is just another type of interface to the computer. Really fancy video cards use that. Different peripheral devices would use a PCIe. So we have the central processing unit, the CPU. And the CPU has two components to it, if you will. It's the arithmetic logic unit, and that does all the hard math. And then you have the control unit. And the control unit is parsing out and sending instructions to be decoded from computer code instructions into mathematical equations and calculations. And then as you can see here, it's kind of a four-step process. And then once that output is performed, that output is then stored in memory. This is a little deeper look at what that process looks like. The central processing unit is fetching and executing. So the commands come in, those commands get decoded, those commands then get executed, stored, and then new commands are fetched out of RAM. Each iteration through here is one CPU clock cycle. All right. Moving on, and hopefully I'm not going too quick. The CPU uses pipelining, and pipelining is combining multiple steps into a single combined process. And it does that to optimize, if you will. So if you can see here, the amount of steps that need to happen when no pipeline is in play, you've got to do 4 different iterations to get a single instruction set done. But when you're using pipeline, you can get the same amount of instructions done in less cycles. One quick thing I want to talk about is pipeline hazards. That's something that might come up. That's when something prevents the pipeline from executing. So any condition that causes a stall in the pipeline would be a hazard. And the other one I want to quickly talk about is speculative execution. So when you hear about all these processor flaws in the media, you know, these, oh, they could hack the Intel processor. Well, what they're doing is they're taking advantage of a feature in the processor called speculative execution. And what this is, in the shortest sense, is it's a way to optimize the processor. It's a way to get more done faster by doing work ahead of time that I may or may not need. So it's like taking the entire CISSP exam, memorizing every last bit of it, and then taking the exam and finding out I didn't need to know every single thing. Having said that, if it's in the book, it's testable. You need to know all of this as much as you can. So the way that the data gets into the processor, if you will, is through interrupts, right? If a CPU is chugging away and it doesn't have another set of instructions, it doesn't know what to do, that a lot of times can cause it to stop operating. Computers need to know what to do next, even if that what to do next is wait. But if we waited for all the commands to get processed that were in queue before allowing the mouse to move, you'd be waiting forever for it to move. So interrupts allow the CPU to temporarily stop processing its current task and pick up a new request. And that looks a little bit like this. So you've got, I move the mouse then says, hey, I need to send a command so I can redraw the cursor somewhere else on the screen. That goes into the interrupt. That then goes to the input-output controller to the CPU, allowing me to move my mouse around and have it show. The CPU, more about it. I hope you guys are learning stuff here. So the key things here is process. Process is an executable program, and its data is loaded into the running memory. Okay, so it's the program is running, data is in memory. That's a process. A thread, also called a lightweight process, or is a child process, and it's where one process has spawned another process. A heavyweight process is called a task. One of the big advantages for threads is they can share memory. So again, orange, really stuff you want to pay attention to here. Process can come in different states. You can have a new process being created. A process could be ready and waiting for execution. A process could be running, or a process could be blocked. A process can be blocked, or a process can be terminated. Generally, when a process is blocked, it's waiting for something. It's waiting for disk. It's waiting for some kind of user interaction, some kind of in-out activity, input-output. It's waiting for. When a process is done running, it terminates. A process or thread that was spawned, or what we call a zombie or orphan thread or process, is where the parent got terminated. So for example, if you had an app that you had open, and then that app opened another app, and then you close the app that opened the other app, that other app becomes a orphaned thing, if you will, an orphaned process. Zombie, right? So remember zombie, remember orphan. I don't know if you guys are Walking Dead fans. I'm a pretty big fan. So the next thing we're going to move on to in the CPU is around multitasking. So multitasking is something we hear a lot about, that we like to think we as humans are good at. We're not as good at it as we think, but computers are great at it. And so they can do multitasking simultaneously. They can run multiple heavyweight processes on a single CPU. And part of that is because of the way the processors these days are architected. But it could also do multiple processing. So it can run multiple processes on a single CPU. And then those come in 2 flavors. You have your symmetric multiprocessing, or SMP, and it's one operating system's managing all CPUs. You have asymmetric multiprocessing, and it's one operating system image per CPU. This will come into play in larger scale computing. You're in a data center. You've got maybe a distributed computing model, that's where these kind of things are going to kind of come in, where you're going to run into symmetric versus asymmetric. Multi-programming is multiple programs running simultaneously on one CPU. I'm doing that right now. I have the streaming program and PowerPoint and Teams and Word and all this other stuff up and running. Then we have multi-threading. And multi-threading is allowing us to run multiple lightweight processes simultaneously on the same CPU. So again, what we're trying to do here is we're trying to get more done with the same hardware. That, however, requires coordination. And so that coordination, a lot of times, a part of that is a watchdog timer to make sure that a system can recover or reboot if a critical process hangs or crashes. Just like you guys experienced at the beginning of this, I ran into a issue where something apparently hung or crashed, and I wasn't able to get the live stream going in time, or on time. And so a watchdog timer, what it's going to do is it's going to look to see if corrective action is needed, and then it's going to take that. And it's either going to do that with complex instruction set or reduced instruction set. So as you can see, CISC and RISC, right? So if you look at how this works, at stage 1, we have, it gets kicked to say, hey, okay, timer's going, timer's going, timer's going, and if nothing happens, the timeout is invoked. Now that can either trigger corrective action, or it can trigger another timer. And then at that timer's expiration, it can either trigger corrective action, or it can trigger another timer. A real world for this is the Netflix Are You Still Watching? Right? That's a watchdog timer. You've been binge watching like Tiger King like it's going out of style. It's 2 o'clock in the morning. You're probably sleeping, so you get the little pop-up. Are you still watching? So that's the same concept here. It's saying something's gone on for too long without some kind of update. I need to kick that and make sure that it's still working well. So now we're going to move into memory addressing. Hope you guys are all keeping up. Memory addressing is how the computer knows where the information is in the memory stack. So as the commands move in and out of memory, sometimes those commands can move from chip to chip. Sometimes those commands can move throughout the memory chip itself and be in different places at different times. And the way that's all kept in check and tracked is through memory addressing. And the ways that you can have memory addressed is direct, indirect, register direct, and register indirect. So let's unpack that for a second. So direct, we're simply adding X to the equation. We're getting a direct interaction. When we're using indirect, we're using something called a pointer, where we are pointing to a different memory space. So the actual command I need doesn't live in the first place I look. I go to the first place and I find a note, and that note says, not home, I'm at Jerry's house down the street. So now I got to go to Jerry's to find what I'm looking for. So that's indirect. It's when the memory, the raw information I need is somewhere other than where I look first. Register direct, again, I'm going directly into the register. And then register indirect, again, I'm going to the register, and the register is saying, that's cool, it's not here, it's over there. So that's, and that's called, pointers. So this is another way to show that. So I think I'm looking in location 301, and then I go to 301, and 301 says to look at 5002, and then I go to 5002, and it says, look at 9000. And then when I look at 9000, I find the data I'm looking for. I find the 302 that I was looking for. So the main thing to understand here is that there's direct, indirect, register direct, and register indirect. And essentially, if it's not direct, then that means that somehow there's a pointer involved. And because of those pointers, we need to have protection. So we don't want other processes getting into the memory space that maybe contains more sensitive data than that other process is allowed to have. Or you could have cross applications trying to access data that has nothing to do with them, and that could cause corruption. But from a security context, we want to protect what's in that memory because it's probably sensitive. And so memory protection can be done in a couple ways. You can do it with hardware segmentation, so physical distance, right? Just like we do for COVID, physical distancing. It's on a completely different hardware, right? You can use virtual memory. So that's using software to try to create a layer. If you remember back to layering, create a layer between the application and the actual hardware memory. So the application goes to look at this virtual address, and behind that is the actual pointer to the hardware. We could also do swapping and paging. And this is where we're going to use the virtual memory to copy contents into a primary location or to or from a secondary memory, not directly addressable by the CPU on disk. So we're able to say it's over there somewhere, and by using virtual memory, we know where the somewhere is, but the CPU is only aware of the virtual location. And then there's kernel accessing memory in swap space is going to cause a page fault, right? So again, you can have corruption issues, you can have stability issues, you can have security issues. So with that, let's move on to BIOS. BIOS, Basic Input Output System. This is the code that runs in firmware. So when you first turn your computer on and it goes beep, and you get the little thing that says post test, and it's sometimes it runs through and does a scan of your memory. Sometimes it doesn't, depends if you have that on or off. But it is the thing that turns on first to then begin the interactions between the processor, the memory, the operating system, the disk, so on and so forth. So the very next thing it does after it does post is it says, okay, what operating system am I running? Where is the boot sector? Where I need a kernel to run. And then it finds that kernel, and then it loads it and executes it, and you get the lovely Windows. So here we're going to look at the CMOS for a second. So if you've been inside this before, you'll see the screen will be familiar to you. This is what happens when you go into your BIOS, and this allows you to configure different things. If you're into PC overclocking, this would be where you would go to overclock things. This is where you go to set up certain security levels for the hardware. And just a quick factoid, CMOS, most people didn't know, and I know for a long time I didn't know, is complementary metal oxide semiconductor. It's also a type of MOSFET is what we call it. So that's a synthetic, metal oxide semiconductor. MOSFETs a lot of times are used for logic functions. So just a little interesting fact there. So security architecture, hardware architecture, right? So we boot the BIOS. We get that initial hardware. Now the CPU knows how to be a CPU, and the RAM knows how to be RAM, and it's good to go. And then we hand that off to the master boot record. Master boot record then says, I know how to be the operating system, and it begins to load itself, and it loads the code that it's been told to load to boot up that operating system. And a lot of times that is called a bootloader. So you go into the bootloader, and then this is the thing that actually goes and loads the 150,000 individual little files and programs needed to actually get it to where you can log into the computer. So in general, master boot record is going to be 512 or more bytes located in the first sector of the hard drive. There's quite a few attacks out there where they like to wipe out the MBR. If you're really good, sometimes you can recreate them. And sometimes if they do other things after that, it's a dead disk. But really, the important part here is to know that there's BIOS, MBRs, active partitions, and bootloaders. So worm is getting a lot of attention these days. Write once, read many. A lot of times you're going to find that in giant data arrays, right? They're going to be the big SANs and NASs and things in the data center. Sometimes they'll have that. There's some new backup solutions on the market that advertise it. But basically it just means that I write it one time and then I read many times. So a standard CD is a type of worm storage, but not a rewritable. So standard CVD, DVD, Blu-ray, these things are write to them one time and then you read from them many. Rewritables don't qualify, and that's basically what you need to know about worm storage for the exam. So write once, read many. TPM. So TPM, or the Trusted Platform Module, is a hardware-based encryption. So it's directly on the motherboard in a lot of cases. And it gives the processor additional security capabilities It can prevent against rootkits and kernel bypass attacks by creating boot integrity. And it can do integrity and disk encryption, which is mainly what it's used for, is platform integrity and disk encryption. And this is what it looks like. So if you open up your computer and you see this little guy here, most likely you have TPM installed. And an interesting tidbit, and this is true for the DoD, and it's growing in popularity. I know some financial institutions that are moving in the same direction, that they require any hardware that they use to have TPM installed, version 1, 2, or higher. So just know that TPM is a thing. Know that it is an international standard. I'm sorry, the group that developed it is international standard. Yeah, TPM. Sorry, I need some water. All right. Hopefully you guys are still hanging in there. We're going to talk about data execution prevention and address space. So one of the oldest tricks in the book is to cause a corruption to memory. Because when I cause a corruption to memory, I give the computer an opportunity to ask me what it would like me to do next. If it doesn't know what to do, the very first thing it's going to do is ask. And in this case, that's done via a stack or heap-based buffer overflow. Very common. Poor coding makes that very easy. If you don't put conditional limits on how big your object can be, buffer overflow is really easy to do. So that's why secure coding matters. But for this purpose, you want to have it enabled within the hardware. And to attempt that the memory locations are not predefined to contain executable content and will not have the ability to have code executed. So what does that look like? So on the left we see a normal stack. We see that there's buffers and return pointers, and it has the arguments, the function call arguments. And then when you go to smash that stack, you go to try to interfere with that, you cause an overflow in the buffer, which then goes to point to the next buffer, and you can have code in that buffer. So when you fill up the memory and it spills out, it becomes empty. It wants to know what to do next, and if there's a command waiting for it, you'll be able to then insert your code directly in the middle of what's going on and start to either redirect commands or take data out of the system. So the kernel is really the heart of any operating system, and it's like a kernel of corn. It's going to generally operate at ring 0. It is your interface between the operating system and the hardware, and they generally come in two primary types. A monolithic kernel, and that's going to be a single executable kernel, and it runs in supervisor mode, and if you want to add anything new to it, you have to completely rebuild it. You have to recompile it. And then there's a microkernel, and that's a modular kernel, and you can add functionality to that via loadable kernel modules. Okay? So the thing to know is kernel comes in two flavors, monolithic and micro. Then we have the reference monitor, and that is a core function of the kernel. That is what is controlling and mediating the access between subjects and objects. You can't bypass it. It's there. It's going to do its job. And that's why things like buffer overflow and stuff like that are so important, because that allows you to kind of get in and cause trouble, where the reference monitor is trying its hardest to make sure that those commands, those objects, those subjects are authorized to do what they're doing on behalf of the user, that the audit trail is present, and that those authorizations are present. So users and file permissions. This is a Linux output of permissions. So if you do an ls-la/etc, you'll see this. It's showing you who's got read, who's got write. So what are those permissions? If we look at this, right? So we have owner. And we can see what the owner has, what the group has, and what the world has. So this owner's got read, write, delete. This one just has, looks like read and delete, if I'm reading that right. Honestly, I forget what X is in Linux. It's been forever since I've been in it. But either way, the important thing to understand here is that users and file permissions users have files, files have permissions, users have permissions. All of that needs to be assigned and mapped. And so the types of permissions are going to depend on the file system being used. Microsoft has their file model of NTFS. That's read, write, modify, and execute. That's what X is, execute. I knew it would come to me. Modify, full control, read, write, execute, modify, in addition to the ability to change permissions. And visually, it looks like this. So if you've ever played around in Microsoft Active Directory or permissions or anything like that, you can see here who are the groups, who are the users, what permissions do they have. So it's important to understand that those permissions can exist and that you need to make sure they're assigned appropriately. So now we're going to move on to virtualization. And virtualization essentially is adding a layer in between. So back to layers. It's all about the layers, right? It reminds me of a Limp Bizkit song, but it's all about the layers. And so virtualization gives us that extra layer. It gives us that software layer between the hardware and the software. It also gives us the ability to run multiple guest operating systems. So now I can use a single physical computer, single physical set of hardware, and I can run many, many different operating systems of different types, depending on the virtualization software I'm using. And I can do that all on a single physical host. Virtualization is going to come in a couple flavors, right? Transparent or full virtualization, and that runs the stock operating system, and no modification to the OS is needed. And then there's para virtualization, which is a modified operating system. So if we think about like VMware, right, or Hyper-V as a host, that's going to be a full. But if we think of, I've got my Windows 10 and I'm just going to spin up a little VMware client on my Windows 10, that's a lot of times going to be a para virtualization. And Brad can correct me on that if I got it wrong, but that's how I recall it. And see if I got it right. Yeah, so basically interacting directly with the virtualization layer or interacting with the host OS. Hypervisors come in a couple flavors, type 1 and type 2. So type 1, again, runs on the host hardware. That's that VMware, that's that Hyper-V hypervisor. And then type 2 runs within the operating system itself. So it's more just like a software application. Now here's another visual around that. So we have here type 1, we can see the hardware, CPU, and memory, and then the hypervisor is the layer above that, and then the guest operating system is the layer above that. And in this case, this is the native operating system, so this would be one of those Windows 10 examples, and then there's a type 2 hypervisor that's running as kind of an application, and then it's interacting back and forth. So what are the benefits? The benefits are it lowers your hardware cost. It lowers your power cost. And it lowers your physical footprint, right? Those are the benefits. There's some scalability benefits if you've got extra hardware available within the system you're running. But basically it's lower cost, lower physical space. For security issues though, you're now adding complexity. And as we remember, complexity is the enemy of good cybersecurity. So we're adding additional complexity into the mix. It is going to be easy for us to bring up new systems, and it's going to be easy to bring up those systems without appropriate checks and balances in place, which then can create security issues, right? Don't want somebody to just be able to run a script and say, yep, I need a brand new web server with all the access that should go with it, and the hypervisor says, great, here's your new guest, with no other check or balance in between. The other main thing to understand from a security issue is that if the host gets compromised, then you can have issues with every guest operating system within that host. So a good practice to follow is not to host systems with varying security sensitivities. Don't put your payment card PCI DSS payment processor on the same server that's hosting your publicly accessible sandbox pen testing app that you made for the kids. Right, you want to keep those separate. I think that's another Offspring song. It's Offspring song. Keep them separated. Right, so that's your takeaway for that. For cloud computing, right? Again, big financial benefit. large economies of scale. It comes in primarily in the flavors of infrastructure as a service. So that's where, you know, Microsoft or Amazon or Google or whoever my cloud provider is giving me access to all this hardware, all this infrastructure, but I've got to set it up, I've got to configure, I've got to do all the other work. Okay? Then there's platform as a service. Now, platform as a service is where the cloud provider has done an extensive amount of configuration work. They've done the install, and I'm just kind of consuming the service. I'm consuming it. Web hosting is a good example, web service hosting. Another good example is database hosting. SQL Server has a platform as a service offering in Azure. And there I'm just consuming. I'm just consuming the service. I don't have to patch it. I don't have to update it. I don't have to, you know, care and feed for it. If I need a new one, I just go and I get a new one. I don't have to do anything else. Then there's software as a service. And software as a service is, you know, it's about as simple as you get, right? Security Studio, right? I don't know if you guys can see it. Security Studio, right? Software as a service. Webmail, Gmail, YouTube, right? You're just using the software. That's all you're doing there. Salesforce is a huge software as a service platform. Then you've got different flavors of cloud. You have private cloud and public cloud. And a private cloud is a cloud that is just yours and yours alone. It's dedicated to you. And a public cloud is a cloud that has multiple users. Another term for that is multi-tenant. Multi-tenant is when you have many different users in that same cloud hosting. So as you can see from the visual here, right, IaaS is those virtual machines, right? Server, storage, network. PaaS is really just providing you the platforms, the database platform, web server platform. SaaS is just, you're consuming it. It's just games, desktops, email, that type of stuff. And then the cloud clients, which would be, you know, your browsers and thin clients and emulators, things like that. So some of the cloud computing security issues are, it's a data center you don't own, right? So number one thing I want you to know about the cloud is it's simply a data center you don't own. You still have to do all of your due diligence and due care. Now that due diligence and due care may come in different forms, like making sure you've got really strict SLAs, making sure that you are limiting the visibility to that cloud environment, making sure you understand that the shared infrastructure that you have, how it works. Are you clear with your vendor what that looks like? You need to make sure that you have the right to audit and assess. You should always have the right to test and pen test. Now, when you do get into public cloud, that gets a little sticky, but there are rules for that. They will help you with that. And then the other thing to understand is that, again, it's a data center you don't own. You can't physically get to it. There could be some geographic issues that you need to be careful about. Zoom just had a heyday of geographic issues because they were using servers in China, right? And servers in China, well, people in America don't want their data on servers in China. So you can geographically need to create separation. So it's important to understand that as well. This one's really cool. I was actually really excited about this slide. So this is BOINC. Rhymes with oink, right? BOINC. And it stands for the Berkeley Open Infrastructure for Network Computing. And what this is basically it's grid computing, distributed computing. It's about using and harnessing many different computers for a single task. Where I found out about this was many years ago when I did a project called SETI at Home, where I would allow my home computer to send unused CPU cycles to SETI to calculate. They would basically send a file to me and use those unused cycles to calculate whether or not the signal they got from space was a space alien, right? They were trying to up the amount of data they could crunch at once. And so that's what BOINC is all about. It's about enabling researchers to tap into the enormous processing power of all of our personal computers around the world. So I encourage you guys to check this out. It's pretty cool. If you can donate some CPU cycles, they are working on stuff that's really cool. Rumor has it they might even use some of this technology to help us solve for COVID. So look into it after the class, but it's pretty sweet. Okay, peer-to-peer computing. Oldest time, at least as old as my time. My first introduction to peer-to-peer computing was Napster. right? That was my introduction to it. BitTorrent, Nutella, so many different flavors, LimeWire, etc., etc. And it's essentially where you're acting as a server and a client. So you could be a client to another node, while at the same time simultaneously being a server to another node. It's decentralized and it's neutral because you're device to device. You're not routing through somebody else's stuff. You're not going through somebody else's data center. You're establishing a network connection between the two devices and then sharing. You got some issues here, right? So peer-to-peer is great, kind of. I've got a few caveats. One of the caveats is that you can have issues with data integrity, data loss. If you are on these services, please be careful. The bad guys hide a lot of ugly stuff out there. You might come across a file that has something in it you didn't want to see. So that's just kind of my coaching on peer-to-peer, kind of a warning. Know that it's a thing. Know that the important part is that you could be a client and a server. It's decentralized, and you can have some data issues, IP issues, and data loss issues. So moving on to thin clients, right? So thin clients, there's not much to them. That's why we call them thin, right? A lot of times it's just a very, very small set of hardware, just enough to be able to connect up to a central server and pull down the application and store just enough data in memory to be able to do the task I need to do. Everything else is stored on the server. Chromebooks are, in my opinion, are a form of thin client. They're not really, so don't take me to the bank on that, but it's in that concept, right, where it's so thin that I'm relying on the horsepower of something else to really handle the load, the lift. Citrix running on a tablet could be potentially, a thin client, right? Diskless workstations. So diskless workstations don't have a disk drive. They're using the network to traverse data back and forth, and all the OS is loaded that way. But they do have their own CPU and memory, right there locally. And then there's some thin client applications, browser-based applications. They run on a full PC. Citrix is probably one of the most well-known. Open Thin Client is another one. But basically, the whole totality of the operating system, everything else lives somewhere else, and I'm just using this application to access it remotely across the network. Internet of Things. So this is expanding daily. As you can see in orange, it is a nightmare. It is absolutely a nightmare. Love IoT. I think there's lots of cool stuff about IoT, but there's a lot of dangers, and the danger comes from the fact that IoT generally is very hard to secure. There's a lot of inconsistencies in the standards of IoT and how it's implemented. There's, your dishwasher, they made it smart and connect to the network, but they didn't think about updating it. So understand that IoT is a thing. Vendors a lot of times don't patch. There's poor customer support. It can, you're gonna have some IoT in your life. Maybe you've got an Alexa or something like that. Just be aware they exist. Be aware they do have unique security risks and they need to be addressed. That's all you need to know for this part of the exam. Emanations. So this is a fun one. Emanations are any type of energy that's escaping the system. And actually, just this week, some researchers created a malware called FANSmitter. So like CPU fan, right? FANSmitter. And they're able to successfully acoustically exfiltrate data from air-gapped computers by modulating the fan, and then having some type of microphone within proximity that allows them to pick up those modulations. They're then able to convert that back to actual data. It's called FANSmitter. It's really fascinating stuff. So just know that even an air-gapped system potentially can have its emanations leaked. And to that point, the government knows this as well, which is why Tempest is the NSA specification and NATO certification referring to the spying on information systems through leaking emanations. So whether that's unintentional radio, electrical signals, sounds, vibrations, and there's been fascinating work done in this space to kind of expose all of this, and just different ways. So check that out. Obviously, they classify a lot of the shielding standards, but several of the levels are public. So now we're going to move on to backdoors. Backdoors are what happens when a developer or a system administrator wants to be able to get into the system quickly, and they don't want to have to go through all the rigor of the security checks. They put it in because for maintenance purposes or something like that. A lot of times. That was, I'm sorry, I'm getting those crossed. It's been a long day and I'm getting blurry here. So the backdoors are the nefarious version. A lot of times a maintenance hook can be exploited to become a backdoor if the maintenance hooks aren't properly addressed. And some developers did intentionally leave backdoors in, not for malicious reasons, but then they were found and exploited by malicious actors. So just know that backdoors exist, and it's a way for somebody to get into the system, subverting the security controls. And then maintenance hooks are part of that design, and really you shouldn't have them in a production system. Get them out, shut them down. But there are still plenty of legacy systems out there that have that stuff in place, so know they exist and deal with it. Okay, so what are we at? Slide 78. Woo, we're not doing too bad on time. Malware or malicious code, right? So we call it malware or malicious software or malicious code. This is all about system vulnerabilities, threats, and countermeasures. So generally speaking, any code that's doing anything that's not authorized on the system or that I don't want it to do is considered malicious, right? If I did not want it to do that thing, it didn't come from the manufacturer, it's behaving in a destructive manner, these things are malicious. A 0-day is an exploit of malicious code in which they have not yet fixed it. The vendor doesn't have a fix. The developers might be working on it, but there's nothing for you to patch or to repair to protect yourself against it. You hear about the 0 days a lot in the news. And then, computer virus, right? That's another term that we hear a lot. Computer viruses don't spread on their own. As a general rule, right? They embed. They want to hang around. They want to collect data and ship it off. They want to steal your passwords, right? And worms are looking to go from system to system to system. That's a general rule. As with all rules, there can be variations. There's different types of computer viruses. So a macro virus is a virus that's written in the same macro language used by the programmers. Most commonly, you're going to see this in Windows, Office, right? That's why there's always that little pop-up that says, hey, do you want to enable macros? Unless you wrote the macro, unless you know what's in the macro, the answer should almost always be no, you don't want to enable them. But that's it's a vector of attack that they can use to get a virus into the system and cause a sequence of actions to happen. And then when the application's opened, the macros go to work and do their dirty deed. A boot sector virus is going to be a virus that infects that boot sector. So remember earlier on we talked about the master boot record. That's what that's doing. It's going to attack that master boot record. It's going to try to infect some of the sector to either elevate its permissions or to try to gain access to the disk or whatever the nefarious activity they've coded that to do. Then you have stealth viruses, and stealth viruses try to avoid detection. So antivirus software uses known signatures to try to trap the virus. So stealth virus is going to know that. It's going to try to change and avoid that detection. Anything that it can do to detect to avoid being detected. Now then we have polymorphic viruses. And polymorphic viruses are going to be complex, right? They're going to create modified versions of themselves to further avoid detection. But they're going to keep all the same basic routines after each infection. They just vary their physical file makeup during each infection. This makes it very hard to find a signature for them. Polymorphic viruses encrypt their codes and use different encryption keys every time. So that's kind of your takeaway on polymorphic. And then multiparte, if I'm pronouncing that right, virus is a virus that attacks both the boot sector and the executable files. So it's going to be, generally they're one or the other. They're either going after the boot sector or they're going after executables, but a multi-part tag could be either or. And hey, viruses, right? So know that they exist. They're not good for you. Try to stay away from them. Worms are going to self-propagate. So they're going to try to execute malicious code. They're going to burn resources. We've had a few famous worms in our life. The Morris worm being the first. I love you. Nimda, Code Red, Melissa. I don't know if you guys remember that, but the I love you letter, right? So it leveraged our humans' need for chain letters. I don't know why that's still a thing. By the way, the bad guys still use chain letters as a way to attack us. So they embedded this code, this VB script, in this I love you letter, and then when people executed it, they got themselves ransomware. And if you've never seen what ransomware looks like, a lot of times this is what's going to pop up. It's going to look something similar to this. It's going to, I've encrypted your stuff, yada, yada. So your important thing to know is that worms move, viruses embed. And then we get on to Trojans. So Trojan generally is going to be a software application that is built for a purpose, but it is not... that's not all it's doing. It's maybe doing something else. I personally have a couple of family members that love the free online games, and they've been hit with Trojans over and over because they download the free game and they're playing the game, but there's a secondary malicious function that's happening. Some of the famous Trojans are Zeus Trojan, CryptoLocker, NetBus, Backorifice, Shadun, which was an Android one. So, Trojan horse. That's exactly what it sounds like. You think you're getting one thing, you wind up getting another. Rootkits. Rootkits are going to replace portions of the kernel or the operating system. They're going to generally operate in ring 3 and ring 0. And the common ones are LS, but there's many others. And essentially a rootkit is just trying to do that. It's trying to get root. It wants to have the highest level of permission possible so that permission can then be exploited to do other things. Antivirus software, so signature-based, right? It's static attacks. There's heuristic-based, and that's looking at things like anomaly and behavior. So, for example, if I've never gone to this website before, ever in my whole life, and now I go to this website, that could be seen as an anomaly of my behavior. Alternatively, if I don't normally push 32 gigs of traffic across the network at 2 in the morning, and all of a sudden my user is pushing 32 gigs of traffic across the network, that could be an anomaly of behavior. There's many different other ways, but the thing to know here, again, is antivirus software basically comes in two flavors, static and heuristic. Server-side attacks or service-side attacks are where you're going after the server itself, you're going after the service itself. And client-side attacks are the downloads. You're trying to get the client to pull down the code onto their machine itself so that it can be executed. Web architecture attacks, web architecture and attacks. So OWASP Top 10, it is evolved. It's still 2017. I checked today, is still the standard that I was able to see that they've published. I believe they are putting out an update soon. But you can see how it's changed since 2013 to 2017, and the main way that it's changed is that they've merged and condensed. They've tried to because as security grows in complexity, we have more things we've got to cover, and they're trying to keep a top 10 list running. So you can see injection, broken authentication, sensitive data exposure, right? These are the top 10 things that you want to be looking for and making sure that you're addressing and protecting when you're having any kind of web architecture. And that takes us on to applets. So applets are just little pieces of code that embed in other software. Plugins, right? Plugins is a way to say applets. You get them from the servers and then they run locally. So if you have any kind of browser plugin, a lot of times that's going to be an applet. Java is going to run its applets inside of the JVM. So inside its little sandbox that it has. It's an object-oriented programming language. You find Java in a lot of places. If you have a car with a navigation system, a lot of times that's wrote in Java. Your DVR, your Blu-ray player, that's Java. Your Fitbit might be run in Java. And then Microsoft's answer to Java was ActiveX. So of course it comes with its own unique set of Microsoft security issues. It's only runs on Microsoft systems, and they use digital certificates to manage security. So if you've ever had an app that popped up and said, hey, ActiveX wants permission to do something, that's where this is coming from. Use it with caution. I'm not the biggest fan of it. XML, so extensive markup language, right? So this is a human-readable, machine-readable set of rules for encoding documents. So it's a really fancy way of tagging. XML looks almost like HTML. They're very similar. They're a tag-based language. So basically at the top, an XML document's generally going to have a tag that declares it as an XML document. That's really all you need to know for that. Service-oriented architecture is going to be, it's basically an architectural pattern, right, in software design that says we're going to use these services and we're going to provide these components and services to other components and services, right? So they do that via communication protocol, typically over a network. Doesn't always have to be. It could be, internal somehow. The service can be used and reused throughout the organization instead of doing a one-off custom job for each person. And some of the concepts are SOAP, REST, DCOM, Corba, and others. And basically those are just ways of doing that interaction, right? It's ways of making calls and requests. SOAP is, I believe it's Simple Object Application Programming. So these are just different types of ways of doing a service-oriented architecture. You just need to know that it's a thing. Polyinstantiation. So polyinstantiation is where you have two different objects, so two instances with the same name. And depending on the security level, one record could have sensitive information and the other one does not. And the user could see or not see that information depending on their level of access, which generally is dictated by the policy that you have. What it does is polyinstantiation allows a database to have multiple records of the same key. A good example would be like a large company's payroll database. There's like 10 Mike Smiths in that database, right? So we need to make a unique key for Mike Smith. Well, Mike Smith works in HR, so Mike Smith can see certain things, but Mike Smith doesn't work in manufacturing, so he can't necessarily see what manufacturing has. Well, that might all be stored in the same database. So we use polyinstantiation to make sure that the user can only see the things they're supposed to be able to see based on their level, but that you don't need different databases to create that segmentation. Mainly it's used in the prevention of interference attacks. So what's an interference? Well, interference is going to be when somebody is messing with the system. They're trying to potentially corrupt data. To figure out if it's going on, you have to use deduction. There's some kind of investigation you have to do and try to look at clues like why did that data change at this weird time or date. You might use polyinstantiation or you might use diffusion to control it. But basically the idea is you want to make sure that people aren't interfering with the data. Then you have aggregation, right? So you're aggregating up. You're asking every single question. There's no need to deduce because you've asked exhaustive amounts of questions, and then you could control that by limiting the number of queries. I'm just going to check in real quick. Moderators, how we doing? We're sitting good, I think. Nobody's talking, so I think we're okay. All right, so continuing on then, because I think we're still good. I don't know, they haven't told me otherwise. All right, good. Next, you guys can tell it's been a long day for me. All right, data mining. So data mining is when we're going to be searching through very large amounts of data, and we're going to do that trying to find a pattern. So if I've been collecting log data for 6 months, and now I'm trying to find a common pattern within that. I'm going to be data mining that. It's used for fraud detection. That's one of the most common ways it's used. It can, however, it can create privacy concerns. So one thing that you need to understand before doing any data mining is, has that data been properly anonymized so that you're not inadvertently creating privacy issues or exposing sensitive PII. And then data analytics is used to determine the baseline of normal behaviors and any deviations from that baseline. And again, generally this is used in the context of looking for misuse or compromise. So am I seeing a deviation of behavior or pattern from the user that would lead me to believe that something suspicious might be going on, either with them as an individual user or with their system account or with their files. And data analytics is how we're going to do that. So defense in depth is, the countermeasure, right? It's got a good crunchy, if you have good defense in depth, you're not going to have a crunchy shell and a GUI center, okay? Because that's not good. You want to have a solid center. You want to have a solid outer ring and a solid outer ring and another ring and another ring. And I'll show you a little bit what that looks like here in a second. You're going to segment. Anybody on the call that talks to me on any kind of regular basis knows I preach segmentation, because the further away the thing is from the other thing, the less likely the two can hurt each other, right? It's that simple. If I can isolate, if I can segment, I can make it way harder for the bad guys to get to where they're going. Document I encourage you guys to look at is the NSA methodology for adversary obstruction. Not always, but a lot of times if it's good enough for the NSA, it's probably good enough for us, right? Because they do go to extraordinary lengths to figure out things like how to obstruct adversaries. So take a look at that. It's some good reading. You're going to have, mobile device defenses. Mobile devices are different to defend. They have different risk profiles. So one of the most common ways that we do that, besides passcode, PIN code, all that stuff that hopefully you know, and if not, call me, I'll tell you what to do to make your phone safe. But in an enterprise setting, we're going to use a software solution that's called mobile device management. And mobile device management effectively is just a software suite that I'm using to control the phones. It gives me certain powers and abilities, ability to remote wipe the phone, ability to revoke permission, an ability to keep my data on a special sector on the phone, inaccessible to the end user if they were to stop being an employee or whatever, for whatever reason. I would then be able to, if I couldn't remote wipe that data, I at least have it encrypted in its own partition. So mobile device management gives you a lot of benefit. There's a whole administrative side to it. It isn't just the technical side, but that is something to know. And then network access control, making sure that only devices that are supposed to be on the network are on the network. It's important to do that for a whole bunch of reasons I'm not going to get into now, but you've heard Evan say it, you've heard Brad say it, now you're going to hear me say it. You got to know what you have. You can't protect what you can't see, right? So knowing what's on your network is super important. Controlling what gets added to that network, super important. And that's where network access control comes into play to help you. And then you've got 802.1x, which is, your wireless, equivalent, if you will, of that network access control. You want to use, cert-based, MAC address-based, things like that. And then the other big thing it does, again, is that remote wipe. That's going to help you in a business setting. That's going to help you, especially now with remote workforce and COVID. I can see mobile device management becoming even a bigger conversation than it's been in the past. So what does layered security look like? So I thought we'd look at this real quick. Don't need to memorize or really even know any of this stuff other than data security, app security, endpoint, network, perimeter, right? Policy and operations. This is all the things one does to protect those mission critical assets. So that's kind of what that looks like. It's a real popular graphic on the internet. All right, are you guys ready for some encryption? The good news is we're nearing the finish line. I'm just going to check moderators again. Guys, we good to go? I think we're good. I don't know. They're quiet tonight. Hopefully they're talking to you guys on the chat because they're definitely quiet on moderator side. So everybody loves this topic, especially Evan. I like this topic a lot. It's a good topic. Encryption is ultimately the number one thing that I think anyone can do to up their security and protect their data from being, if stolen, used, right? An encrypted hard drive is as good as an empty hard drive. If you don't have the key, it's as good as dead. So these are the key terms. So now I'm going to borrow from Brad. You guys are going to need to memorize this. This is one of these memorization ones, okay? So cryptology is the science of secure communications. Cryptography is the creation of messages whose meaning is hidden. Cryptoanalysis is the science of breaking encrypted messages so that you can learn what they mean. Cryptology encompasses both cryptography and cryptoanalysis, right? Because it's the whole science. The cipher is a cryptographic algorithm, okay? Plaintext is an unencrypted message. And what you see on the screen right now is plaintext. Ciphertext is what happens to plaintext after a cipher is applied, and that creates an encrypted message. Encryption is the process that converts the plaintext to ciphertext, and decryption is the reverse of that. It turns the ciphertext back into a plaintext. Okay? Memorize it. All of this matters. All of this is very likely to be on the test in some form or another. So the other things that are important to understand are confusion, diffusion, substitution, and permutation. I'm not sure who invented these terms. I think they wanted to add as many vowels as possible to some of this stuff. Because I've got confusion. I'm currently suffering from confusion because I'm trying to understand encryption, right? So confusion is the relationship between the plaintext and the ciphertext. It should be as confusing as possible. I shouldn't be able to easily figure out what you wrote. Pig, for those of you that know Pig Latin does not lead to good confusion. Pig Latin has bad confusion. I know what you're saying because you haven't confused me well. You haven't randomized it. You haven't made it hard for me to decipher what is going on. Okay? Diffusion is the order of the plaintext. It should be diffused or dispersed in the ciphertext. If your plaintext is, hello, my name is Ryan, and your encryption, your cipher, encrypts that at the top, no matter how much encryption comes after, no matter how much padding, how much extra stuff you put in there, if the whole message is at the top, it's going to be much easier to crack. So the idea is to space that out, to put like a letter or a word, and then more randomized confusion, and then another letter and a word, and more randomized confusion, right? Substitution is the replacing of one character for another. This is what provides you diffusion. And we'll get into a little bit more of that as we go into the history of this stuff. I got some visuals that'll help make that make sense. Permutation, also called transposition, provides confusion by rearranging the characters of the plaintext anagram style. Okay? Substitution and permutation are often combined, or permutation, and strong encryption destroys patterns. So any sign of non-randomness, cryptanalysis is going to latch right onto that. They're going to say, it's actually how we caught the Nazis, and I'll talk more about that in a minute, but you really want to make it as gobbledygook as you can. So the harder it is to figure out what's going on, the harder it is to find patterns, the more secure that encryption is going to be. Or that cryptography, right? So cryptographic strength, right? Good encryption is strong. It's strong. It's hard to break. Ideally, it's impossible to decode it without the decoder ring. Maybe you guys are I'm from the 80s. If you ate Captain Crunch, you got a secret decoder ring at some point, right? It was pretty easy to convert ciphers back and forth, but you had to have the decoder ring to do it. The work factor, and again, if it's an orange, you probably want to know it. The work factor is describing how long it's going to take to break the system? How much effort, how much work effort do I got to put into this to break it without a key? Because if it's easy enough to guess, I can do enough random guesses over enough time, I will get the right answer. There's only so many letters in the alphabet, right? What you'll hear about in the next couple of coming weeks and months is the growing quantum computing, and how quantum computing is going to break all the ciphers and it's going to break encryption. Well, that's because what quantum computing does is it's taken the work factor from decades down to minutes. So that's the important part to understand there. Work factor is how long it takes. The secrecy of cryptographic algorithm does not provide strength. So Kirchhoff's principle, right, basically says that no matter what else is wrong with the system, the secrecy, right? So even if everything's public, I don't mean to say wrong, if everything is public about the system, the secrecy shouldn't be. You guys should Google that. I was going to tell you more about that, but I think it's a good homework assignment. I think you should learn who this gentleman is and what he did. And it's Kirchhoff, I think, or Kirchhoff. I don't know. I've never heard anyone pronounce it the same way, so I'm not sure what the correct pronunciation is. Maybe the monitors can put a phonetics in the chat for you. So remember I said we've got some pictures. So here's those pictures, right? So now let's talk ciphers for a second. Let's talk monoalphabetic cipher. And that's just a single letter substitution where I just say, okay, E becomes X, F becomes I, right? It's just swapping one for the other. A polyalphabetic cipher is using many alphabets. So mono, poly, right? One to one, one to many. So now I've got to use the polycipher. I say this time around it's going to be E, and this time around it's going to be X. And so I can make it so that you have to, now back to layers, right? We talked about layers. So this is another form of layers. We're making it harder to guess. You see over here where it says ROT. ROT actually stands for rotation. And we'll talk a little bit more about that here in a minute. So one of the common methods that crypto analysts use to figure out where to start, if you will, is trying to do frequency analysis on the letters. So knowing the frequency of a letter and its ratio of occurrence in language allows you to then start to unpack that. So we know that E occurs the most. So we start looking for all the E's. Where are all the places that E would make sense for a letter, right? Where, and then we go down in that frequency. So we walk down and we say, okay, can we figure out any of the words simply by using the frequency of that letter? We know it's going to show up so many times, more so than the others. So if we can find E, then maybe we can find T, and then so on and so forth as they go down in their frequency of occurrence. It's generally used as an aid in breaking classical ciphers. Doesn't work as good on some of the new stuff. The first known recorded explanation of frequency analysis, or really for that matter, any kind of crypto analysis, was given in the 9th century by Al-Kindi. He was an Arab mathematician. Interesting guy. You can read up on him. All right, we're going to talk about the exclusive OR logic gate. So it's, how do I want to explain this? Okay, so it's really common component of some of the more complex ciphers. Basically, by itself, using any kind of repeating key or just a simple XOR cipher doesn't take very long to break using frequency analysis. Remember frequency analysis? So it's not very hard to break it using that. But if I use it in conjunction with other operators, it can start to become computationally, expensive to figure out what's going on. So I want to, avoid any kind of repeating. I want to use the key for the operation and not necessarily the whole data. And sometimes it's used where there's no requirement of security, if you will. A lot of times we see XOR ciphers used in malware because they're trying to obfuscate. They're trying to make it hard to figure out what they're doing. And I'm sure our coaches and moderators can expand upon that further. But you need to know it exists, right? And it's used to do some type of encryption. I wouldn't personally use it myself because it is very easy to break, but it's there. So let's do some history here. We're gonna probably finish right on time. I like this. All right, so the history of cryptography. Well, just like our children, the Egyptians figured out if they talk in pictures, people can't understand what they're saying. So for those of you teenagers at home, the kids using emojis, we're actually going back to the invention of cryptography, hieroglyphics. So they were using, photos to represent. And if you didn't know, like most of us don't, I'm not fluent in Egyptian hieroglyphics. I have no idea what this thing on the screen says. I'm sure it says, "Hey, Ra, you're doing a great job talking to a blank wall of Lego figures." But that's what it is. That's what it does, and it was really popular. I'm actually going to have to update this slide to add 2020 because emojis have brought it back. Then we had the Spartan Cytail. I think I'm pronouncing that right. I have no idea. But it was used by the Spartans, and it was really interesting. What they did is they took this wooden rod, and then they'd wrap the paper around it, and depending on the diameter of that rod, they would... So the sender and the receiver would have matching diameters, right? So if I wanted to encrypt a message, I take a 3-inch round rod, I wrap my message around it in a linear order, or lengthwise, right? Do it in lengthwise, and then I unwrap it, and I send my message. Now, the receiver, they're aware of the size of rod that I used, and so they use that same size rod, and they wrap the paper in the same order, and then they can read my message. And the way that I protect that is by changing the diameter of the rod. That would change whether how that message was decrypted. And then they just unwound it and sent. So that's how they did it in the old days. And then we started to get a little bit better with stuff. So we came up with the Caesar cipher and rotation ciphers. So remember back to that one I showed you before where it said ROT13. It's about the number of times, the number of rotations each letter gets forwarded. So kind of like a safe. So if I say that A is D on pass 1, but A becomes B on pass 2, and then A becomes E on pass 3, I've done a ROT3. I've done a 3 rotation. And you can rotate to however you want. One of the common ones was ROT13. Well, so it's 13 iterations. I wouldn't use that one any longer myself unless you're playing with the kids at home learning encryption and cryptography, because it's pretty well broken, but we did rely on it for quite some time to protect things like bulletin board systems and Usenet. Then we have the Vengere cipher. I think it's Vengere. I don't know. I'm not French. I know one of the students here, Rod, I'm calling you out. Tell the people how to pronounce this one. Polyalphabetic cipher was named after Blaise de Vengere. And he was some French guy that lived in the 16th century, right? Math guy. He created the Vengere square, which is the alphabet repeated 26 times. So this is what it looks like. So back to that rotation, right? So A on the first 0 rot becomes B on rot 1, C on rot 2, and D on rot 3. So that's your rot. That's your rotation. And this is your square. Okay, so you can see 26 iterations of the alphabet, and then you line up your ciphers to find your correct letters. All right, now we have the cipher disk. So this was 2 concentric disks, each with an alphabet. So you can see there's an outer alphabet, and then there's an inner alphabet. You could do monoalphabetic and polyalphabetic encryption. But you would have to agree up front with someone what the fixed offset was. So you would come to an understanding to say, okay, D really means S. And then as long as you guys had that agreed fixed offset, then you would agree on how many rotations, and you'd be good to go. For polyalphabetic encryptions, the parties, agreed again to have that fixed offset, and then they agreed to turn the wheel a certain number of times. This was invented in 1466 or 1467, who knows, by Leon Battista Alberti. And Alberti is considered the inventor of the polyalphabetic cipher, and that was used for a very, very long time because it was a very effective form of encryption. Then we came along, and in the 1790s, Thomas Jefferson created a cipher system called the Jefferson's disk, and he was comprised of 36 wooden disks, each with 26 letters in random order along the edge, and then the order of the disks that are put on is the cipher key. I hope you guys are keeping up here. This is all important stuff. Most of this will be mentioned in some form or another on the exam. Then you have a book cipher and a running key cipher. So I read a study the other day that said that the intelligence community is actually considering going back to book cipher because it has become easier and easier to break encryption, frankly, to just trick a user into installing malware and gaining access to the system. Some of the really sensitive stuff, they're going back to book cipher. And book cipher is where, we've pre-established the text we're going to use. So for this example, I'll say Harry Potter, right? So the first book of Harry Potter. And we're going to start on page number 22, word number 4, letter 1. And then we're going to use that to encode. So you see the example here where it says attack at dawn, we the people. Well, once A plus W, right, gave us X, and T plus E is Y, right? Now we've got an encrypted message. Benedict Arnold used book ciphers. But yeah, you agree on the text and the source, page number, line, and word offset, and then you can just use the book to do the encoding. A running key cipher, instead of using whole words, uses modulus math to add letters to each other. So that's what this is. We're adding letters to get a different letter. All right. Code books. So code books were books that already had pre-established codes in them, and you were given a code word for people, location, and terms. So if those code words came up in communications, you would have the translation for what those words were. A one-time use pad uses identical pairs of pads that they have all been set up to have the exact same set of random characters with a set amount of characters per page, and then you use one page to encrypt the data, and the other end of the equation, the other user, right, they use the exact same page to do the decryption, then you throw both pages away. If you never reuse those pages, right, you're never supposed to reuse them. Well, use once, hence the one-time pad. And it is the only encryption method currently known to be mathematically proven to be secure, only if these three conditions are met. The characters on the pad are truly random, the pads are kept physically secure, and no page is ever reused. The very first one-time pad was the Vernam cipher. Again, probably going to be on the exam. It's the first known use of a one-time pad, and it was named after Gilbert Vernam. He was an employee of AT&T and Bell Laboratories. And his cipher used bits, and this is pre-computers. He used bits, which was common in teletypes, and the one-time bit pads were XOR'd to be plain text bits. So if you remember back, XOR, right, it goes back to this time. Project Verona, it was undertaken by the United States in the United Kingdom to do cryptoanalysis to break the KGB's encryption. So they had their national security agency, that's the equivalent of, KGB is the Soviet Union's equivalent of our NSA. So they did this Project Verona to try to break their encryptions in the 40s, and they used one-time pads for sensitive transmission. So technically that should have made us unable to break their code. However, they violated one of the 3 rules, and they reused a pad. And once that happened, we were able to break. And they were able to decrypt many famous names. And so again, think about how the attackers look at this stuff, right? They're going to look for names and common things. That's why codebooks exist. That's why obfuscation exists. they did not, this is not testable, but wanted to highlight the dangers of not following the rules for the correct use of a one-time pad. I encourage all you guys to watch these. Myself, I love the Imitation Game. Not only do I get to say Benedict Cumberbatch, which I think is a pretty sweet name, really great movie. I think the guy did a fantastic job. Great actor, great movie, pretty historically accurate. U-571 is another great movie. That's about the U.S. is getting their hands on the Enigma machine, and then All the Queen's Men. And I'll admit I haven't seen that one yet, but it's on my short list to watch. But check these out. It'll help you get your head kind of wrapped around this a little bit better. Okay, so some of the machines that came out of that era, if you will, is the Herbin machine and Purple. And they used rotors. They used electronic rotors, kind of like big typewriters, and you'd punch them, and then the rotors would rotate to different characters, and that was how they were doing kind of their cryptographic encryption. And then those were common in World War I, World War II, and were in use up until the 1950s. Probably the most famous cryptography machine of them all is the Enigma machine. If you guys don't know about the Enigma machine, look into it. I'm not going to read all this because we are getting close on time, and I'd like to finish for you guys so you can go about your getting a nap so you can keep your studies. But this was really, really hard to break, and it actually, the way we were able to kind of break that was Alan Turing. So if you go back to here, the Imitation Game is about how we were trying to crack the Enigma. And we eventually were able to do that when we got our hands on one. And we figured out some things that allowed us to find the word Hitler, because the Nazis signed every communication with Hail Hitler, and that's ultimately how we caught him. Sigma, this will be on the exam, is a rotor machine that we invented, so it was our version of the Enigma. We took the Enigma apart. We thought, hey, we could do a better job. To the best of anyone's knowledge, it was never broken. Purple was used by the Japanese. This is as much of it that is left that we're aware of. In the 40s, we were able to figure out if we had decoded their code properly by sending some false information. So we sent them misinformation, which then caused them to send a communication that allowed us to confirm that was real. And they were using that for Midway Island. They were calling it AF. We thought that AF was the code word, so we sent a bogus message, and then they sure enough said, oh, yep, there's a problem with AF, so that confirmed it for us. All right, next one here, Wassenaar Agreement. So more will come up in next week's class, but there are some agreements, there are some legal things you're going to need to know. This is one of them. It was created in 1996, kind of as the Soviet Union was going through their change, and it relaxed a lot of the restrictions on exporting cryptography. Cryptography, in some cases, can be considered a weapon or a controlled export. And so just understand that certain technologies are considered export controlled, and the Wassenaar agreements allowed for some sharing of some of that information. I'm going to check in real quick. Guys, are we good here? Let's see. Moderators, anything left before I kind of roll us in for the close here? Just give them a second to respond. I know there's a slight delay. All right. Well, looks like we're good to go there. So I'm gonna go ahead and close us out of this. So with that, that's it. That's enough. I know I'm tired. I think you guys might be too. Appreciate it. We're not gonna have any class on Monday. This is a great opportunity for you guys to study, catch up. Please do use those study tips. They'll help you out a lot. We're going to pick it up on Wednesday with even more encryption. I think Evan is actually leading that one. Yep, Evan's going to be leading that. Yay! We should be up to about page 160. And come prepared with questions. We'll follow up, obviously, with everything that happened in the chat. Be safe, be healthy, and have have yourself a really great night, guys. Thank you so much. I'm going to leave the slides up for a bit here, and we'll take it from there.